Welcome, children. This is Stoichiometry and Mole concept, one of the chapters of grade 10 ICSC. But I have included molecular weight and its calculation, percentage of compounds, or percentage of elements in compounds, which are done in grade 9 and grade 8 also. So it caters to the need of grade 8 and 9 children too. Then we have problems based on chemical equations, that is stoichiometry, which involves mole concept, under which we have to cover Gay-Lussac's law of combining volumes, Avogadro's law, and empirical formula and its relation with the molecular formula and the ensuing calculations. So we go over all these things one by one and clear up the concepts. So let us start with molecular weight. Molecular weight, the next topic which we must know very clearly because it will be used for stoichiometric problems. The molecular mass of a compound is found by comparison with the mass of 1/12 of the mass of carbon-12 isotope of carbon atom. The molecular mass expressed in grams is known as molecular weight of a compound. It is calculated by adding up the individual atomic masses of the atoms present in the molecule of a compound and expressing the value in grams. So grams and AMU, they will tell you what you are dealing with. If it is AMU, you are dealing with atomic mass or molecular mass. If grams is the unit, you will be dealing with the molecular weight of the compound. So here are some examples done for you. Find the molecular weight of Na2SO4, sodium sulfate. The given molecule contains 2 atoms of sodium, 1 atom of sulfur, and 4 atoms of oxygen. Remember, I have used the atomic weights here, but they are always given. They are always given alongside the question or at the head of the question paper. If you are solving problems from a book, it must be given in periodic table. So go to periodic table and you can look up the atomic weights. Therefore, the molecular weight will be 2 into 23. 23 is the atomic weight of sodium. So there are 2 sodiums, 2 into 23 plus 1 into 32, that is sulfur, plus 4 into 16, that is oxygen. And this opens up to 2 into 23, 46, 1 into 32 is 32, and 4 into 16 is 64. You add them up and you get 142 grams. So the molecular weight of sodium sulfate is 142 grams. Some more examples. Calculate the molecular weight of Na2CO3.10H2O given Na equals 23, C equals 12, O equals 16, and H equals 1. As I said earlier, atomic weights or atomic numbers are given. They need not be learned by rote. You don't have to memorize them. It is given in the question. So the molecular weight is 2 into 23, 1 into 12, 10 into 2, and 13 into 16, which is 46 plus 12 plus 20 plus 208. 13 into 16 is 208, and it adds up to 286. So 286 is the molecular weight of one molecule of sodium carbonate, decahydrate, or 1 molecule of washing soda. This is washing soda. And we have 20 atoms of hydrogen. So it is 10 into 2, 20. We have 10 into 2, 20. And 10 plus 3, 13. 3 oxygens here and 10 oxygens here. So 13 into 16. 10 plus 3 is 13 into 16. Again, we have another compound. This is a complex compound. Find the molecular weight of K4FeCN6 given K equals 39, Fe is 56, carbon 12, and nitrogen is 14. So 4 potassium atoms, 4 into 39 plus 1 into 56 because 1 iron atom, 6 into 12 carbon because this 6 outside the bracket is for all the elements present inside the bracket. So 6 into 12 for carbon and 6 into 14 for nitrogen, and that goes up to 368. It adds up to 368. Finding composition of a compound, of a molecule of a compound, or molecular weight of or percentage composition of a compound, both means the same thing. First, calculate the molecular weight of the given compound as shown earlier. Then percentage of element follows this formula: weight of the element in the molecule divided by molecular weight into 100. Some examples are here. Find the percentage of carbon in C6H12O6, which is glucose. There are 6 atoms of glucose in the molecule of glucose. So total weight of carbon 6 into 12, 72. Molecular weight of glucose is 180, as has been calculated here using this formula. And percentage of carbon, applying this formula, we have found out as 72 divided by 180 into 100. So 0.4 into 100 is 40. 72 by 180 is 0.4. Find the percentage of iron in iron 3 chloride. Iron equals 56, chlorine equals 35.5. So iron 3 chloride, we have to write the formula first. So iron is in valency 3, and therefore we have FeCl3. If it were 2, it would have been FeCl2, but this time it is FeCl3. So for 1 iron 56 plus 3 into 35.5 for 3 chlorines, that adds up to 56 plus 106.5, and the total is 162.5. Percentage of iron is, applying the formula, 56 is the weight of iron, 162 is the weight of iron chloride, 162.5, sorry, and that into 100 will give you 34.46. Find the percentage of carbonate and water. Well, this type of problems are also asked in washing soda. The molecular weight of washing soda is 286 grams. Molecular weight of carbonate only is 12 plus 48. 48 for 3 oxygens. 3 into 16 is 48. Total 60. Weight of water is 10 into 18. H2O is equal to 18. H2O is 18. It is 16 plus 2 into 1, so that is 18. And 18 into 10 molecules we have, so it is 180. So weight of water is 180 grams in the compound. Percentage of carbonate 60 divided by 286, the total weight, into 100, 20.97, roughly 21%. Percentage of water equals 180 divided by 286 into 100, that is 62.94%, roughly 63. Therefore, percentage of sodium by difference can be found out as follows: 100 minus 20.97, the percentage of carbonate, plus 62.94, the percentage of water. So 100 minus 83.91 is 16.01. Now comes stoichiometry. Now, stoichiometry is the relationship between weights of reactants and products before, during, and at the completion of the reaction. Mole. It is the quantity of substance constituted by 6.022 into 10 to the power 23. Some books take it as 6.023, but I have checked on Google, and in IB textbooks it is 6.022 into 10 to the power 23 particles. The weight of 6.022 into 10 to the power 23 atoms of any element is its molecular weight. Molecular weight or atomic weight. If it is atoms, it is atomic weight. If it is molecules, it is molecular weight. If it is molecules. So the particles can be anything: molecules, atoms, ions, electrons, protons, neutrons, whatever it is, but they have to be subatomic particles. The weight of 6.022 into 10 to the power 23 atoms of any element or molecules of any compound. If it is atoms, it is atomic weight. If it is molecules, it is molecular weight. The molar volume of a gas is 22.4 dm cube or 22.4 liters. 1 dm cube is equal to 1 liter at STP. And that is the volume occupied by 1 mole of any gas at STP. So we can write an equation connecting all these values together as 1 mole equals 6.022 into 10 to the power 23 molecules is 1 molecular weight. This is for compounds and bimolecular gases which have 2 molecules in them, like oxygen, hydrogen, nitrogen, fluorine, chlorine, bromine, iodine. 22.4 liters at STP if gas. 1 mole equals 6.022 into 10 to the power 23 atoms equals 1 atomic weight equals 22.4 liters at STP if monoatomic gas like hydrogen, neon, argon, krypton, xenon. And if it is atomic element like iron, copper, then it is 1 atomic weight. The short form of mole is MOL, and 6.022 into 10 to the power 23 is known as Avogadro's number, and it is designated as Na, N subscript capital A. This is capital A. So this stands for Avogadro's number, which is 6.022 into 10 to the power 23. Remember, in some books it is 6.023 as well. It doesn't matter. It doesn't matter. There are plenty of zeros behind this. Well, it doesn't matter whether it's 23 or 22. But the standard that I have seen in IB and in CBSE books is 6.022. So we take 6.022 for calculations. For calculation, it may be simplified even to 6.0 or 6.02 only. So no need to worry about that. A stoichiometry contains the stoichiometric problems are based on molecular weight calculation, writing balanced equation, and the application of the mole concept. They are of following types: weight relationship. One weight will be given, the other weight may be asked. Weight volume relationship. Weight of a compound is given, the volume of the gas evolved is asked. Volume relationship based on Gay-Lussac's law of combining volumes. Mole weight relationship, mole of one compound is given and weight of another compound is to be found by relation. Mole volume relationship, as we just saw, 1 mole is equal to 22.4 liters or dm cube at STP. So that relation has to be used in mole volume calculations involving Avogadro's law. So this is what I have in short for stoichiometry part 1. I'll be coming very soon, that is by tomorrow evening, with stoichiometry part 2, in which the calculations based on these 1, 2, 3, 4, and 5 types of relations in a given chemical equation will be shown. So thank you. Do comment. Comments are most welcome. That helps me to improve the contents. And please study with the help of these videos and get your marks flourishing. Get your performance in the class flourishing. Thank you and have a nice day.